In 2-1, we talked a lot about two types of polynomials. What types did we talk about? Okay, 2-1, go back a section before that. Y'all come on. We did two types of polynomials. One of them was a trinomial or something. But what was it called? Linear was one of them. We did the scatter plots. We did linear regression lines. We did a lot with linear functions. What was another type of polynomial that we did a lot with?
Quadratic.
Yes.
Yes, sir.
And quadratics. We did a lot with the quadratics where we completed the square to find the vertex. We shifted, we shrank, we stretched. We did a lot of stuff with it. What degree is a linear function? What's the degree? Degree means what? Degree is the highest exponent, and it is 1. What's the degree of a quadratic? 2. So what we're going to talk about in this lesson is we are really going to talk about some higher degree polynomials, like polynomials of degree 3. What are those called? Somebody was going to say cubics. How about a degree of 4? Quartic. That's right, quartic.
Yes, sir.
And we'll even get a little bit higher than that. Well, 5, 6, and so on. Okay? When I have a polynomial, this is just reviewing a little bit more. I write them in order of their what? Exponents. So maybe I have 5x to the 4th minus 6x cubed. Do I have to have every single exponent? Is it still a polynomial if I don't? Yes. That's still a polynomial. What's the type of polynomial there? Quartic. It is a quartic. What is the leading coefficient? 5. What else do you know about this without graphing it?
If it's like if it was backwards, like on the grade that you gave us, it was x and then x cubed. Does the leading coefficient
You have to switch them around. So if you had it, if you got one, and this was on your quiz yesterday, if you got it where it was x minus 3x squared, you would need to switch those around to standard form, because we put it in order of the degree, order of the exponent, excuse me. What else do you know about that polynomial? It's going up. Why is it going up? It's positive. What else do you know? Well, now you're getting into quadratics, so maybe not, but if it was a quadratic, yes. What else do you know, though? No, that's quadratic. It does not matter. It does not matter. Constant. What else does that tell you? The constant's two things. It's the constant and the close. Yes. Y-intercept. Because we're going to do this some today, tell me how else, if it wasn't in standard form like this, if you had any polynomial in the whole wide world and you needed to find the y-intercept, how could you also go about doing that? In other words, let's say I had 2 times x minus 5 squared minus 18. How could I find the y-intercept there? And I know I'm kind of jumping around here. I'm just trying to fill in holes to make sure we're ready for the lesson today. That's vertex form of a quadratic.
You gotta find the opposite of that.
What happens at every y-intercept?
You gotta find one space is y, and then you find y.
All right, let me do it this way. Y-intercepts are where they cross the y-axis, right? What are the coordinates of this point? This one right here, what's the coordinates? 0, 1. What's the coordinates of this point? 0, -3. What's the coordinates of this point? What happens every time you cross the y-axis? The x is 0. Right? We all see that. So if you don't know the y-intercept because it's in a different form and I need to find it, a good way to do that is to let x equal 0 and solve from there. So here, if x is 0, I'm going to have to go get a battery for this thing. Then y equals 2 times 0 minus 5 squared minus 18. And I could solve from there. And I'm running through this fast because we're going to get into this some more, but I wanted you to understand why we would be doing it this way if it's in another form, okay? So here, 2 times 25 minus 18. What's 50 minus 18? Thank you. Crosses the y-axis at 32 is the y. Even though that's not the number on the end because it is in a different form. Does that make sense, everybody? Y'all have the Halloween hangover, apparently. Sugar has all worn off, and now you're zonked. Going back to polynomials for just a minute. What do you call each piece in a polynomial? So this, and this, and this, and this. What are those called? Terms. Thank you. These are called terms. Okay, each of those is a monomial term. When all the exponents are lined up in order, that's called what? Yes, standard form. This is all I told you. This is kind of a recap before I get into the new stuff. Okay, I think we're ready. All right, let's talk about some higher degree polynomials. I want you to take out your calculator for just a second. This is a little activity I was going to have you do and turn in for a grade, but we're going to do it together. I want you to graph two things. I got two different equations here. Okay. The first one is standard form. It's just a single term. The second one is it's in a little bit different form, right? I want you to graph them on the same graph, and we're going to talk about what we see. So take out your calculator, put them both in, put one in y1 and put one in y2. And on your calculator, if you want, you can even change what the lines themselves look like. If you come over here, you can make one darker than the other if you want to, so you can tell the difference in the two.
What is how you do it?
Scroll over, beside the y equals. But we're going to do x to the 5th x minus 3. What's the what? Jackson, why aren't you in your group? No, move back to your group. Without changing these so that you see which one's which one do you think is which?
That one, the one on the axis is the x.
Plus 2.
The one, okay, so Forever says the one on the axis right here in the middle, that's the x to the 5th.
And the other one is
the other
minus
one.
3.
Okay, why do you say that?
Because
What makes you say that?
You want to make this play now? You want to solve it? Move right 3 and up.
Y is where it's placed. That's what I wanted you to get at. That's what I knew. That's what y'all were getting at. Did y'all hear what they said? Look at this equation.
Because if it's minus.
If you think back to your transformations, right? This is right 3 and up 2. This one is right 3 and up 2 from that one. Does that make sense? So we're still talking about those transformations. We're just doing it with some much bigger functions now. Okay? Not just x cubed like we were doing, but notice the similarities in the x cubed, that cubic function that we did, and in this one. It's just got a little bit funkier things going on in here, but it's the general shape of it's the same, especially the end behavior of it, going off in opposite directions. And that's going to be important in just a minute. All right, let me give you 2 more to look at. That was easy. Y'all got that one way too fast. That's a good thing, though. That means you understood the transformations. What if I add something like this? What I really want to do is compare on what happens when we start adding these functions together. So now I got 3. Go. Tell me what you found as you graphed these. Okay, one of them was a straight line. All right, I'm gonna do x to the 5th, and I want you to watch how I'm fixing to graph these. All right, I'm gonna do. What was the other one? X to the 5th plus x. X to the 5th plus x, and the last one was x. All right, I'm going to do the x to the 5th in bold. You can tell me what, Jerome? I hope you can. Oh, no, my calculator just froze. All right, I restarted. All right, what I'm going to do, I'm going to put x to the 5th. I'm going to bold that. Should be able to tell the rest, but that's okay. I think I'll do this one. I'll do the little dot on it so you can see it being drawn. All right, let's graph it and see what happens. Oh, no, that's a... It's not working with me today. Okay. All right, bold. There's my x to the 5th. Oh, look. Oh, man, the other one's too bold to see. Okay. I was trying to make it nice for y'all to see. I'm going to just reset it back to normal. What did y'all find when you graphed it normally on yours?
X to the 5th and the other x to the 5th.
They're really close together. What's the only difference that you see? Or what are the differences that you see? No, in the graph. All right, x to the 5th. There's when I added x, and there's the line that goes through. What's the relationship there? If I compare it to all of those, let me zoom in a little bit for you. Let's go -5, 5. Let's go -2, 2. There's the first. There's the second. And there's the line. What do you notice? Watch it draw one more time. I don't know if I can, let's see. Oh my God, oh my God. A nasty one. Those are those little roaches.
Why do you think
right, watch it draw one more time. Watch it draw. Especially watch the middle, okay? Gosh, dog it. All right, I'm gonna just do -4. All right, here we go. There's the first one. Here's the second. Watch the line. Look in the middle. Do you see that in the middle of the graph it's taking on the characteristics of the line, but on the outsides it's kind of taking on the characteristics of the fifth function, okay? When we added it together. That's kind of what I wanted you to see there. All right, here's what I want you to do. I want you on your paper right now to take just a minute. Remember when we talked about maximums and minimums? I want you to sketch a graph that has, let's see, 4 different extrema. And label what kind they are. So your extrema can be anything you want. They can be maximums, they can be minimums, they can be absolute, or they can be relative, whatever you want. But sketch a graph. I'm going to have somebody come up here and sketch what they drew. And we'll talk about what kind it has. Max, min can be absolute or relative. Who wants to come up? Do I spin? Okay, come draw us on here. You know it on there or this, whatever you want to do.
Oh. 1, 2, 3, 4. That's got 5.
Oh, no.
Yeah,
I know. You're supposed to draw one with 4.
Alright, then erase this curve. Oh, you erased it off.
You said erase this curve. Oh, you're talking about just that one part. Okay, go ahead.
1, 2, 3, 4.
There you go. I'll get it. Tell me what it has. I said I'd get it. Tell me what it has.
Nah, I got it. Don't worry about it.
What does it have? What kind of max? Where? Absolute and relative. Which one is which?
The first one is absolute.
Oh, is it though?
Yeah, pretty sure.
No.
Is it the highest? It's relative, exactly. If the n goes on forever, if I have, and think about this before you answer, if I have 4 extrema, maxes and mins, will I ever have an absolute anything? No. Because if I've got 4, the ends are going off in opposite directions. You saw he tried to draw one where the ends went off in the same direction the first time, but it had 5, right? All right. So that means this one is also a relative max. What else do you see?
Would that be relative?
Yes, the 2 relative minimums, that's right. Max, minimum. How many zeros does this have?
4.
Let me ask you this.
Yes.
If you had to guess the degree of this polynomial, what might you guess?
5. I would guess like a
Why would you guess 5?
because it's got 5 to it.
That's a nice conjecture. Why would you guess 6?
Because I like the number 6.
Oh my goodness.
I would guess like
What?
All right, let me show you this. And I'm not going to give you the answer just yet. This is a line. It has a degree of what? 1. This is a quadratic. It has a degree of. This is a cubic. It has a degree of. Oh. What might clue you in there? Those extreme points there, those extrema. So this is leading up to a theorem is what I wanted you to see, and I wanted you to kind of get it on your own before I just gave it to you. You are right, this would be a degree of 5 here. The theorem is actually the local extrema theorem and zeros of polynomials. You don't have to know the name of it. What I do want you to know, though, is that And I'm going to just say theorem here. You know what a theorem is? You remember from geometry probably? You got theorem to death. Okay. The degree of the polynomial tells us about zeros. And extrema. And here's how it does that. If the degree is, we'll say n because we're going to generalize it. Okay? That means that the polynomial has, come on, at most, meaning it can't have any more than n zeros. So the degree of the polynomial, it could have up to that many zeros. If we said that that one before was a degree of 5, how many zeros did it have? The one that Hampton drew, 5, right? And it can have at most, now look back at that one and think, and tell me what you think I'm going to say about the zeros. I mean about the extrema. How many extrema did it have?
4.
4 extrema, but we said it was a degree probably of 5. So the most extrema it has is n minus 1. Okay, so that can tell us a lot about the graph without actually graphing it, just looking. Y'all okay so far? I'm going to do one more thing and I'll be done. Yes. We're having all this fun in here. I don't know why you want to leave. Hampton. Here's what I want you to do. I want you to think about this with me for just a minute. We're going to talk about in behavior a little bit more. We're going to try to build on what we've already talked about within behavior. And that's kind of what this whole lesson does, is build on things we already know. We talked about in behavior if we see a graph, right? And we can look at the graph and we can tell what the in behavior is by just looking at it. But what if we just look at the equation and we want to know the in behavior? So I want you to think about a couple of different polynomials, and I want us to graph them and look at them and see if we can make a generalization. So the first one I want you to look at is, let's do this, 2x to the third. Graph that on your calculator and tell me the in behavior. And we got a lot of these to do, so we'll pick it up after the first couple. Remember, we now do limit notation. Infinity. So you're saying the right side of the graph goes up. Okay? Whenever you graph this, it's a cubic. It's going to look kind of like this, right? The limit. Is that what you got when you graphed it? Something like that? Thank you. How about this one?
So, I think the music goes up.
Mm-hmm.
Maybe the music goes down.
Mm-hmm. Almost.
Well, what is zero?
What zeros? That's infinity. All right, so this one, what does that negative in front do to the graph? Maybe it looks so. Ah, that's the same one. I'm sorry. So as I go towards positive infinity, the graph is going which way? Negative infinity. And as x approaches negative infinity, the graph is going. Okay. Here's what I'm going to do. I've done the first two with you. I'm going to have you finish this little exploration activity to determine end behavior, and then let me stop this.